Good morning, students. Today we will continue the third part of our the discussion what we are having on sets. So first I'll start discussing with De Morgan's law. So De Morgan's law does that. Suppose I have two sets A and B. And B, if I make a union of this thing, A union B, and that prime, that is the complement. If I make the complement, then the result is A prime intersection B prime. And the other way, if I make A intersection B prime, that becomes A prime union B prime. These two are the very important rule, and that is known as De Morgan's law. Next topic what we are going to discuss is called difference between two sets. What is meant by that? It is the difference, that is also an operation. Okay, the difference of two sets is something. Let's look at by means of a Venn diagram. Suppose I have two sets A and B. The difference of two sets, these two sets A and B, is denoted by A minus B. What is this? A minus B is a set. It contains the element of A which are not present in B. That means what? Let's understand by means of Venn diagram. Venn diagram is a very important tool here to understand this. Suppose this is the universal set of these two sets A and B, and I have the set A here and the set B here. So this is set B and this is set A. Understood? Now A minus B is the element of A which are not present in B. That means this is the portion. What I am writing here in that red lines. So this is the set which is represented by A minus B. Now what will be its definition in the set builder form? It's like this. A minus B is equal to X such that X belongs to A but X doesn't belongs to B. Remember, this word but is very important here. Okay, sometimes this word is also interchanged with the word and, like A minus B equal to X such that X belongs to A and X doesn't belongs to B. But is the most important word here. That we'll see. If you use and, then also it's fine, but and is also may mix up with A intersection B. Okay, so that is called the difference between two sets. Okay, so let's have some properties. Let's see some properties of A minus B. We can have it here. Okay, suppose A is a subset of B, then what it implies? A minus B. If A is a subset of B, then A minus B is a null set. Why? Because A is completely within B. So A minus B doesn't make any sense. Means it is not possible to have any element in A which is not a element of B. That means A minus B is of no sense. So we can say A minus B equal to phi, the null set. Clear? Thank you. Next one is that if A intersection B is equal to phi, that means this portion A intersection B equal to phi, then A minus B is nothing but A. Alright? So this implies A minus B is equal to A. I hope you understood this one. It tells that here that I have two sets. One is A here and the B is here. They are disjoint sets because A intersection B is phi. So A minus B is not possible to have any element of B in A. So A minus B equal to A. Correct? Okay. The next one is that A minus B, we can also write that A intersection B prime. You can try it at your end and see how this is going on. Okay, this is very simple. Now the next one is that very important property, A minus B intersection C. Okay, let's first say that A minus B union C is equal to A minus B intersection A minus C. A minus B union C is equal to A minus B intersection A minus C. That means this union is actually getting here as an intersection. In the other way, if I write A minus B intersection C is equal to A minus B union A minus C. Clear? Alright, thank you. The next topic what we are going to discuss is about the symmetric difference of two sets. So we just add another word called symmetric. Symmetric difference of two sets. What is meant by that? So it is denoted by the symbol called A. This is the symbol of symmetric difference. That is equal to A minus B union B minus A. That is called symmetric difference between two sets A and B. Let's have a look into it by means of a pictorial form in Venn diagram, how it makes sense. Suppose this is the universal set and this is the universal set U. This is the set A and this is the set B. Okay. So what is A minus B? A minus B is this part. Right? And what is B minus A? B minus A is this part. So, what we see is that the region covered by that green lines and the region covered by the blue lines, the union of these two is known as the symmetric difference. So in other way, we can see that A symmetric difference B is nothing but A union B minus A intersection B. The other way we can say, right? Because this is the A union B part, entire part is the A union B minus this part, which is A intersection B. So we can write that A symmetric difference B is equal to A union B minus A intersection B. Clear? So what will be the symmetric difference of A and phi? Phi is the empty set. So A symmetric difference phi is nothing but the set A, right? So we can write that A symmetric difference, the null set or empty set or void set, all are synonym, is equal to the set A. Sorry. Then what is the symmetric difference between the two sets where both the sets are equal? The other way I can say the symmetric difference on the same set. That means A symmetric difference A is nothing but the empty set, because if we consider A and A, so A minus A is phi and union A minus A equal to phi. Phi union phi is nothing but phi. So what I was saying is that according to this definition, if I put A in place of B, I will get A minus A union A minus A. A minus A is nothing but phi, that is equal to phi union phi is equal to phi. Correct? Okay. The symmetric difference is commutative in nature. That means A symmetric difference B is equal to B symmetric difference A. That is also associative in nature. That means A symmetric difference B symmetric difference C is equal to A symmetric difference B symmetric difference C. Right? Another interesting property is that we can write the same thing. We have earlier we defined the two forms, another one, two different forms of asymmetric difference B, and we can also write asymmetric difference B is equal to A intersection B prime, right? A intersection B prime union A prime intersection B. That you can make an experiment using Venn diagram, you will find it out. Our next point of discussion is what is a finite set and what is an infinite set. Very simple. A set is said to be a finite set if it has finite number of elements. Here the examples are the set of all rivers in India, the set of all students in a class, the set of all prime numbers less than 30, like this. That means the elements we can count. Here one point has to be noted, that if there are two elements in the same name, we can only make it a count of only one. What does it mean? If a set has elements called 1, 2, 2, 3, we should not write like that. We should write 1, 2 and 3. That means the repetition of 2 should be ignored. Only once we consider that element 2. On the other hand, the infinite set is the set whose elements are not countable. What are the examples? The set of real numbers. You really cannot count, right? If I tell you to find the number of real numbers between 1 and 2, it is infinite. The set of points in a plane, the set of straight lines in a plane, it is infinite number. That's why it is called the infinite set. Okay? Sure. What you understood is that the finite means finite set. It means elements are countable, an infinite set elements are not countable. Now, in the case of a finite set, where the number of elements are finite, means we can count, then the number of elements present in a set, the number, is called the cardinality of the set. So cardinality applies mainly for the finite set. Okay. So what I am saying is that in case of finite set, okay, cardinality is equal to the number of elements in the set. So if the set is A and it has m number of elements, so its cardinality is defined by n of A, and which is equal to m. Correct? And the moment the cardinality is coming into the picture, there are very interesting formulas which is absolutely important to solve some problems later we'll see. Okay, what are the formulas? Here are the formulas, the very important formulas. Okay, that is called n of A union B is equal to, that means if I have two sets A and B, the cardinality of the set A union B, that means the number of elements present in A union B, we can express in this way. It is n of A plus n of B minus n of A intersection B. So n of A union B is equal to n of A plus n of B minus n of A intersection B. Now if I have three sets A, B and C, what is the formula? Here it goes. In case I have three sets A, B, C, then n of A union B union C is equal to n of A plus n of B plus n of C minus n of A intersection B plus n of B intersection C plus n of C intersection A plus n of A intersection B intersection C. Let me repeat. N of A union B union C is equal to n of A plus n of B plus n of C. Then minus is common to what? Common to the three terms. In minus of n of A intersection B plus n of B intersection C plus n of C intersection A plus n of A intersection B intersection C. Remember, these two formulas are extremely important while solving some problems on set, basically where the sets are related with numbers. Okay, we'll see later how it is important. Any question? Thank you. Our next topic is power set. You know, power set is also known as set of sets. Why this second definition, synonym, set of sets? We'll see in few minutes. Suppose I have a set S and it contains two elements, A and B. Now, the power set of the set S is nothing but a set. Obviously, it is a power set, it is a set. The power set of the set S is a set contains all the possible subsets of the set S. I repeat, the power set of a set S is a set contains all the possible subsets of the set S. Let's see by means of this example. If this set S contains two elements A and B, what are the possible subsets? The possible subsets are phi, which is null set, then a subset A, the elements is only A, then B, and then finally the entire set A is actually AB. In this case, this is actually an improper subset of the set S because this is the S itself. Phi, null set is a subset of any set, only A. A is the element, that is also a subset of this set. B is also a subset of this set. So, power set is denoted by P of that set S. So, P of S should contain these are the elements: phi, A, B, echo. There is an interesting formula here, observation. If a set S contains n elements, its power set contains 2 power n elements. The proof of this theorem we will see later. Okay, what is that? So here you see the set contains 2 elements, so its power set contains 2 power 2, that is 4 elements, 1, 2, 3 and 4. So the conclusion is, if a set contains n elements, its power set contains 2 power n elements. Very important formula that will come into the picture on several proofs of other formulas. This is very important, and proof of this proof of this theorem we will see later, especially when we will discuss about the principle of mathematical induction. Okay, now if you take 3 elements, A is equal to ABC, okay, or 1, 2, 3, whatever, you will find that its power set should contain 2 to the power 3, that is 8 elements. Want to see? Okay, let's have a look. Suppose the set S contains 3 elements, 1, 2 and 3. So its power set should contain, first one is phi, the null set, then 1, 2, 3, then 1 and 2, 2 and 3, 3 and 1, and finally the entire set is 1, 2 and 3. So it contains 2 to the power 3, that is 8 elements. The first element, second element, third element, fourth element, fifth element, sixth element, seventh element, and finally the eighth element. So this is an improper subset of the set S because this is the S itself and all the other sets are proper.